So let us start today's lecture. So we have seen that in the previous lecture or lectures we have seen the interaction picture, and we have also derived if this is a state in the interaction picture which is time dependent, and this is related to a state in the Heisenberg picture, that is a state at time t is equal to 0. I'm not writing suffix h anymore. You should just remember that this is at, I have not written any time t, so this is at time t is equal to 0. Therefore, this state is the state in the Heisenberg representation. And this is the operator. I'm omitting the hat notation on top. This is an operator, which is a unitary operator, which relates the states in the two different representations. And we have, in the previous lecture, we have obtained an expression for this unitary operator, and it was of this form. It was a time ordered product of e to the power of minus I by h bar integral 0 to t v hat. And once again, I'm not writing v hat here. This is basically an operator, or let me, it's better to write it at notation. So this is this unitary operator, which connects the two states in the states in the two different representations. And you know what this series, what this e to the power of time order thing of this exponential means. And now what we shall do today is we shall introduce another operator. So this is the state psi t in the interaction representation. This you can write it down as t comma t naught psi t naught. So now what I do is I introduce another operator, which is s hat t comma t naught, which actually relates, and we should also remember that t is greater than t naught. This actually relates a state in the interaction picture at time t naught to a state in the interaction picture at a later time t. So that is why I put the condition t greater than t naught. So we have this operator s hat t comma t naught. So this is how this operator is defined. And psi t naught at I, this we can write it down as s hat t comma t naught, and this we can write it down as u hat t naught psi, right? Because of this. Okay. Now, if you just compare this with this, we can immediately see that u hat t is equal to s hat t comma t naught u hat. So this is the relation that we get. Remember that t is greater than t naught. So by comparing this relation with this relation, it immediately follows that this is equal to this. Now we know that this is a unitary operator. Therefore, what I can do is u hat t, I can just operate from the right with u dagger t naught. This will give us s hat t naught, because u hat t naught, u dagger t naught is identity, because u is an unitary operator, and therefore s hat t comma t naught is basically u hat t u dagger t naught. And you can immediately check that this operator that we have introduced, s hat t comma t naught, is an unitary operator. That is very easy to check, because s hat t comma t naught, if you take a dagger from this, from here, you will get, this is basically. So what we need to do is we need to calculate s hat dagger, s hat t comma t naught, that is equal to, you can see that S hat dagger is basically U hat. So S hat is this, so dagger will be U hat T naught. U hat dagger T, and then S hat, which is U hat T, U hat dagger T naught. This is identity, and then this comes, this is equal to identity. Therefore, this is identity, and similarly, you can show that S and S dagger is also identity. Therefore, S hat is an unitary operator. So that is quite straightforward. And you can show some other properties also, some other interesting properties of this operator S hat. So let's see what these are. So if I take S hat, so the first immediate property that you can see is that if you take T comma T, so S hat T comma T will be U hat T, U dagger T, therefore that is identity, because U is unitary. So this is one property, S hat T comma T is identity. Just as U hat, you remember U hat at 0, U hat at 0 is identity. Similarly, S hat T comma T, whenever the arguments are same, it is basically identity operator. And then we take, let us take S hat dagger, the dagger of S hat operator. So if you take the dagger of that, then this will give us U hat T naught, U hat dagger T. But this by definition is nothing but S hat T naught comma T. So what it does is that it just dagger just swaps the arguments. So this is another property that is quite interesting. Then you can write down the third property, which is S hat T comma T prime, S hat T prime comma T double prime, that is equal to S hat T prime comma T double prime, where we have T is greater than T prime greater than T double prime. Okay? So we have this. So this is another property that we have, and you can prove it easily. It's not that difficult to prove. So let us start from this line. Let us start from this equation, the defining relation for this S hat operator. So here you can just make this T comma T prime, then this will be T prime, where T is greater than T prime. Now psi T prime, you can write it down as T comma T prime. This we can write it down as S hat T prime comma T double prime, psi double prime. Reaction picture where T prime is now greater than T double prime. And in one shot, we can also write S hat T comma T double prime, psi T double prime. This, so where T is greater than T double prime. Compare this relation with this relation, this immediately follows. So S hat T comma T double prime will be equal to S hat T comma T prime comma T double prime. This is another nice property of this operator. And then we have the dynamical evolution equation for this operator. So let me see whether this is working or not. It's not working. So we have this relation, that is S hat T comma T naught is U hat T, U hat dagger T naught. Now let us take a del T of this S hat T comma T naught. To take a del T of this, then this del T acts only on this thing. So this is U hat del t and dagger not multiplied by IH bar, so this gives you IH bar, but IH bar del t you had t, that is the dynamical evolution equation of for the operator u had t, and that is basically nothing but v had I t, you had t, and this thing is you had t, you had dagger t naught is nothing but s hat t comma t naught, and therefore you have the dynamical evolution equation for this operator s hat. It looks the same, it is exactly the same as the time dependent Schrodinger equation, and where this v hat it is basically the interaction part of the Hamiltonian in the interaction picture. So this is the dynamical evolution of equation for the operator s hat t comma t naught, and you can now begin to start solving this equation with the condition that s hat t naught comma t naught is identity operator, and if you do that, if you try to solve it in the same way as we did it for the operator u hat t, you remember the way in which we solved the differential equation. If you proceed in the same way, then you'll be able to show that you can write down a formal solution for this operator s hat t comma t naught, and it will be the time order product of e to the power minus I by h bar t naught to t. Initially, remember that in u had t it was from 0 to t, but now it is from t naught to t. We had I t1. This is the formal solution of the operator s hat t comma t naught. Is this okay? Is this clear? Do you have any questions with this new operator that we have introduced today, which is s hat?
Sir, the exponential form that we have written for s hat, we are writing it in analogy with mu hat t, right, sir?
Not analogy. If you just solve it, you will get this.
Okay.
This is not any analogy. The way in which we have solved the differential equation for u hat t,
Yes.
we proceed exactly in the same way for this from this differential equation that we wrote down, that is this is equal to this. This is the differential equation for s hat t on t naught. So now you just start to solve this differential equation in exactly the same way as you did it for the operator u hat t. Then you will actually land up to this formal solution. Instead of 0 to t, the only difference in this case will be that it will be the integral will be from t naught to t. So I would suggest that you please try to work this out. This is a homework. So please try to work this out. Is it okay?
Sir,
It looks like S and U are the same operator, only the time region is different and almost everything are same.
Yes, almost everything is same. See, S is related. I have given you the relation which relates the operator S to the operator U. This is the relation.
Okay.
Right?
Yes, sir.
The only see another property that I would like to give you. You see what you can see what is the precise relation between S and U. You just put t naught is equal to 0. Then what will happen? S at t comma 0 is u hat t, u dagger 0. U dagger 0 is what?
Identity.
Identity operator. This is the relation between the unitary operator u and s hat. S hat t comma 0 is nothing but u hat t. Okay?
Okay, sir.
Good. See, you should remember one thing, that all the representations, you have three different representations. The Heisenberg representation, the Schrodinger representation, and the Dirac representation, which is the interaction representation. All these three representations are equivalent at time t is equal to 0. They match at time t is equal to 0. We should remember this thing. The Heisenberg representation, in the Heisenberg representation, states are time independent, so it is already at time t is equal to 0. There is no time there. And the interaction representation Kate and the Schrodinger representation Kate, they are time dependent, but at time t is equal to 0, they are identical. So if you take the interaction representation at time t is equal to 0, so that means it is the same as the Heisenberg representation. There is no time. So all the three representations are identical at time t is equal to 0. You should remember this.
Sir? Yeah. The form of A set in terms of U dagger, can we just write the form by multiplying U hat T into U dagger T naught?
I didn't get the question. Repeat once more.
I am saying, sir, we know the form of U hat T and U hat dagger T naught, and we know that T greater than T0. By multiplying the form of U hat and U dagger T, can we just write the time ordering of e to the power minus I by h bar?
A very good question. Good question. Okay, let us do it.
Okay, sir.
Let's do it. Let's see what happens. It's a very nice question. So S hat, in fact, we would have done it later. You have asked the question a little bit earlier. So let us see what happens. We have seen that S hat T comma T naught is related to the U operators in this way, where T is greater than T naught. Now this is equal to, what is U hat T? U hat T is time order product of e to the power of minus I by h bar integral 0 to t v hat I t1 dt1. This is what U hat T is.
Yes.
Right?
Yes, sir.
And what is U hat dagger T? This is time order product. Since you have a dagger, it will be e to the power of plus I by h bar integration from 0 to t naught v hat I t1 dt1. Right?
Yes.
Is that okay? But this, we can write it down as, this is 0 to t and this is 0 to t naught. But this we can write it down as, we can just put a minus sign on top. We can change the integration from t naught to 0. Right? This thing we have just changed the plus sign to a minus sign and changed it from t naught to 0. That is fine.
Yes, sir.
Now since t is greater than t naught, this time is greater than t naught. Therefore, you can combine this expression as e to the power of minus I by h bar from t naught to t, because it is already time ordered. Because t is a later time than t naught. Therefore, you can combine this as minus I by h bar t naught to t v hat I t1 t1 time ordered product, which is this. Does that answer your question, Sean?
Yes, sir.
You wanted to get this without solving the differential equation, just by putting in the values of U hat T. So we have put in the values of U hat T and proved that S hat T comma T naught is indeed this. Okay?
Okay, sir.
Good. So now with this formalism in hand, let us see what we can actually do with this formalism, or why is this formalism important to us. But I would actually suggest you to prove this result by solving the differential equation. Please prove the result by solving the differential equation and get to the same answer. So do it as a homework. So now let us again see where can we apply this full formalism or the full technology that we have learned. So let us once again consider the Hamiltonian. So this is our Hamiltonian, which contains a free part H naught and which contains an interacting part. This is the interaction part. And let this Hamiltonian, this thing that we have written down here, let it be defined at time t is equal to 0. So this is at time t is equal to 0. So by time t is equal to 0, I mean that this Hamiltonian is time independent. Okay? But there is an interaction piece, and that interaction piece actually makes it difficult to calculate what the ground state of this Hamiltonian is, of the full interacting theory is. So this is what makes it difficult. This is the interacting part, and this term is responsible for finding out, makes it difficult to find out what the exact ground state of this full Hamiltonian H is. And let the exact ground state of this full Hamiltonian be denoted. This is a time independent state. This is time independent because we are looking at time t is equal to 0, say. So this is time independent. And this is the ground state, that is the state of minimum energy of the full Hamiltonian H. And let that energy be E naught, say. And it is what I am saying is that it is very difficult to calculate what this E naught is and what this omega state is. It's difficult to find out the ground state energy of the full Hamiltonian and also the ground state wave function or ground state ket of this full Hamiltonian H hat, because it contains interactions. Let us also denote the state of minimum energy or the ground state of this Hamiltonian H naught by this state ket 0. And we know that this is 0. This state has energy 0. Because it is the state of minimum energy. Here, obviously, it is a vacuum state, and in field theory, you should be careful because there is 0-point energy which is infinite. But you have, what I am assuming is that you have normal ordered the thing, the Hamiltonian, the 0-point energy is gone, and you define this to be you define 0 as the minimum of your energy. So this ket 0 is the vacuum state which has energy 0. And this is the vacuum state or the state of minimum energy of only the free part of the Hamiltonian. And free part of the Hamiltonian, you can actually calculate what this vacuum state is. It is easy to calculate. It's not difficult. Right? The free part Hamiltonian is always exactly solvable, and you can find out the wave functions in quantum mechanics. You can find out the wave functions and the energy eigenvalues of the free Hamiltonian. That can be done easily. Okay. Now, also another thing to remind you is that H hat naught do not commute with V hat. Which actually means that H hat also do not commute with V hat. So they do not commute. Okay. What we want to find is the following quantity. Let us do it for a scalar field, for a real scalar field, and we want to find this quantity. Okay. Are you with me, or is it okay?
Yes, sir.
Okay. If you have any problems, you can just stop me. We want to calculate this thing. You should remember that we have already proven a result in our earlier discussions that the vacuum expectation value of the time ordered product of two field operators to free field operators. So there the vacuum state is the state of minimum energy of this Hamiltonian H hat naught. That means it is Ket 0. So you should remember that this where these are free fields, not interacting fields. Okay? These are free field operators. So you should remember that this was equal to nothing but the Feynman property, I delta f x minus 1. It basically says that what is the probability of a particle at the position y, at the space-time position y, to go to a space-time position x at a later time, if it moves in the vacuum of the free field Hamiltonian. So that is what it roughly means. This is the physical meaning of this quantity. But now we want to find out the same quantity, but not in the vacuum of the free field Hamiltonian, but rather in the vacuum of the interacting Hamiltonian, the full interacting theory. So this is something like you want to find out a quantity which tells you, which asks the following, that what is the probability of a particle to move from spatial position y vector at some time y0 to some spatial position x vector at some later time x0, moving in the interacting vacuum of the full interacting theory, moving in the vacuum of the full interacting theory. This is what we want to calculate. Is the problem clear? This is very important. You should understand this part. This is the quantity that we want to calculate. But we have already calculated a quantity for free fields. Here there were no interactions and we calculated it. It was the Feynman propagator. But here, this quantity is actually very, very difficult to calculate. This is very difficult to calculate. Why? Because of the simple reason that you don't know this state. The state of minimum energy of the full interacting Hamiltonian, we don't know that state. So how will you calculate such a quantity? And not only that, these fields are the fields which make up this Hamiltonian H hat. So these are fields, interacting fields. So you don't know what these are. So in other words, these are field operators. You know that these are operators. So these field operators are time dependent. So they are in the Heisenberg representation. And you don't know what their forms are because you don't know how they evolve in the Heisenberg picture. Because in principle you should be able to calculate it, but it is very difficult to calculate. Because in the Heisenberg picture, these fields basically evolve by the full Hamiltonian. In the Heisenberg picture, they are time dependent and they evolve by the full Hamiltonian H hat. And the full Hamiltonian contains the interaction. Therefore, it will be very difficult to calculate an expression for this of how does it evolve in the Heisenberg picture. You will not be able to write down some neat mathematical expressions for this operator. So it is difficult to know what this phi is. How to know phi, we need to know how do they evolve in time t. We don't know what this omega is. So there is no way by which you can calculate a simple vacuum expectation value of time order product of two operators. This is very difficult to calculate. But you know the corresponding result here. For free fields, mind you, this notation may be a bit confusing. This field phi is not this field phi. This field phi is when you don't have any interactions. Your v hat is 0. For free field Hamiltonian, this is the field phi. So it will be, I will change the notation in a moment. Or it is better, just remove this for the time being. what we need to calculate, what we need to know is how can we calculate such a quantity. And to do that, let us now proceed in the following way. Let us consider this phi at time t is equal to 0 x vector to be a field configuration at time t is equal to 0. So this is at time t is equal to 0. This is a field configuration at time t is equal to 0. In the Heisenberg picture, how will this field configuration evolve? It will evolve in the following way: phi t comma x vector. It will evolve via the full Hamiltonian, which is time independent because this is defined at time t is equal to 0. It will evolve like this. Right? In the Heisenberg picture, this field configuration at time t is equal to 0 evolves in this way via the full Hamiltonian H hat. And what will be the equation of motion for this field operator? It will be the standard Heisenberg equation of motion for the operators. Now let us see. Let us define this operator phi 0 t comma x vector and define it in this way. What is this operator phi 0 t comma x? This is the operator in the interaction picture. Why? Because this operator evolves via the free field Hamiltonian H hat naught. So a field configuration at time t is equal to 0 evolves if it evolves via the free field Hamiltonian H hat naught. Then the operator corresponding operator that you get is the operator in the interaction picture. So this operator, since it is the interaction picture operator, this operator will evolve via the which operator? It will evolve via this operator, the free field Hamiltonian H hat naught, because the Heisenberg equation of motion for an operator defined in this way is nothing but I h bar d phi dt is equal to phi naught comma h hat naught commutator. So it evolves via the operator h hat naught, via the free field operator h hat naught. This operator we shall call the free field operator. Free field operator. Because this is the operator which evolves via h hat naught. This is the free field operator or the operator in the interaction picture. Is it okay? Is this point clear?
Yes, sir.
Good. Now you see that this operator is in the Heisenberg picture. It evolves since it evolves via the full Hamiltonian H hat. But phi 0 x vector, you can write it like in this way. From this equation, phi 0 x is what? Let me write it down. This is just this term. But phi 0 x is nothing but e to the power of minus I by h bar h hat naught t phi naught t comma x I by h bar h naught t, and then this term. Right? So I have just replaced phi 0 x in terms of phi naught tx here, and we get this expression. But what is this equal to? What is this operator? This operator is nothing but u hat t. And what is this operator? This operator is nothing but u hat dagger t. phi naught t comma x, phi naught. Sorry, correct. This is u hat. So phi t comma x is basically related to the free field operator. The operator in the interaction picture phi 0 t comma x, which evolves via the free field Hamiltonian, is related to this phi naught and the unitary operator u hat t that we defined earlier. And you know, how does this unitary operator evolve? How does this unitary operator evolve? The unitary operator evolves via the interaction Hamiltonian in the interaction picture. So it evolves via v hat I comma t. So this is defined at time t is equal to 0. And this operator in the interaction picture is nothing but, it will be defined like this. V hat I t. So it evolves via the Hamiltonian H naught. And that is how this operator also evolves, u hat t. So now you can see that this operator in the Heisenberg picture, which is time dependent, it has been expressed in terms of free field operators, that is operators which evolve via the free field Hamiltonian H hat naught, and also operators which evolve via the interaction picture Hamiltonian, interaction Hamiltonian, or interacting part of the Hamiltonian, full Hamiltonian, that is V hat, in the interaction picture. So now you can see what this phi t comma x is related to this in this way. And this makes our life simple, and we shall see how does it make our life simple. So do you have any questions at this point? Do you have any questions? Is it clear?
Yes, sir.
What we have done. So in summary, what we have done is we have related the field operator in the Heisenberg representation to free field operators, because they evolve by the free field Hamiltonian, and therefore you know what their mode expansions are. That is the advantage. You know what these fields are, and also you know what these are, because you know what V hat is, and therefore this operator evolves via the V hat in the interaction picture. And the interaction picture operator actually evolves via the free field Hamiltonian. So you know what this right hand side is. Now you can write down exact, at least some neat mathematical expressions for this operator phi tx. You can write down some neat mathematical expressions for this operator in the Heisenberg picture. So you know what this is, at least. You know what this is. So what is phi tx or phi x? This thing is actually phi of t comma x vector, because this x is 4 vector. So this is t comma x, and this phi y is also phi. Okay, let me write this down as x0, and this is y0 comma y vector. So you know what this phi x and phi y is in terms of this. So you can put it over here, take the time ordering of that. But now what we need to know in order to calculate this full thing, we need to know what this omega is, which is a time independent state, because it is at time t is equal to 0, and we want to calculate, and this is the state of minimum energy of this full interacting theory, and therefore it is very difficult to calculate. So what should be our strategy? Just as in this case, this phi x, we have tried to relate it in terms of free field operators and free field Hamiltonian. Here also, we should try to relate this omega in terms of the state of minimum energy of the free Hamiltonian. That is what we should try to do. Is this clear? So if you need to calculate, if you want to calculate this, we now know what this 5x and 5y is, because this is the expression for that. You just need to know what this omega is. And if you can tell me what this omega is, then we can proceed to calculate that quantity. Okay. So if you are okay with this, then let us consider an expression of this form. We have actually calculated these kind of expressions earlier also in our path integral course. When we were discussing path integrals in the previous semester, we were actually trying to look at these expressions of this form. So let us once again look at consider an expression of this form. This H hat is the full Hamiltonian, defined at time t is equal to 0, and let this n be eigenstates of this full Hamiltonian, which we don't know. It's difficult to calculate this because there are interactions. So in principle, you don't know what Kn is. So what is n is equal to 0? This state is basically omega, right? This is the omega state, which is nothing but n is equal to 0. And Kn are the eigenstates of the full Hamiltonian. The n is equal to 0 state is the state of minimum energy, which we have denoted earlier by ket omega. So let us now see what this is, and also the states obey the standard completeness relations. We have the standard completeness relation, and let us now see what this is. E to the power this 0. We can now put in completeness thing here. Remember, we have done similar kind of calculations earlier. This is this thing. This we can write it down as, we can just isolate the n is equal to 0 state. This will give us t 0 0, and then we have 0. So this will be get 0. So this is nothing but n is equal to 0 means omega, then omega 0. So that is what the n is equal to 0 term is. And then we have terms where n is not equal to 0. The same thing with n not equal to 0. We have just isolated the n is equal to 0 term from here. So therefore, this is equal to I've just taken this term common. This is what we have. So this is this quantity, t to the power of minus I by h bar Hamiltonian t. So this is this quantity. Is this okay?
Sir, that inner product with omega and 0, should not that be 1? I mean, they are the same state.
Which one?
Uh, that first term you have written kate omega, then inner product with omega and 0. I mean, that is the same state, 0 and omega.
This one.
Yes.
No, this is not the same state. See, this keten, I've defined it earlier for you. It is here. N is equal to 0 is this. This N is
Yes.
equal to 0 state is omega, and this is the ground state of the full Hamiltonian. But ket 0 is the ground state of only the free part of the Hamiltonian. So that is not one. Okay. I've defined it earlier for you. So now what we do is we take a limit t going to infinity into 1 minus I epsilon, where epsilon approaches 0 from the positive side. So this basically means that epsilon is a small positive number. So see, En, these are energies of the excited states, therefore En minus E0 is positive when n is greater than 0. So this quantity is always positive, and now you take this limit t going to infinity into 1 minus I epsilon. So this term, all these terms will go away, and therefore this will be nothing but limit t tending to infinity into 1 minus I epsilon e to the power of minus I by h bar e naught t 0. So what we have managed to do is we have actually isolated the ground state. We have actually managed to isolate the ground state of the full interacting theory. And let us see what we can do further. So what we have now is, so this limit, this thing is equal to this thing. Therefore, we can write this as omega is nothing but limit. You can go back to your earlier notes in the previous semester where we did a similar kind of thing.
Sir, I didn't understand the previous thing. I mean,
Which
the
one?
limit. I mean, how?
I mentioned this
Yes,
thing
it is 1
we have
minus I epsilon.
yes. So what will it do? If you take this in that limit, this term will go to 0.
But sir, it's I infinite. I mean, that is a oscillatory.
No, you see, there is a I epsilon. That I epsilon minus I, and this minus I. So there will be a decaying damping term in the expression. There will be a damping.
Oh, okay, yes.
Minus I and minus.
Yes, sir.
This we have done it earlier in the path integral course. Remember, a similar kind of thing we have also done when we were discussing path integrals in quantum mechanics in the previous semester. We have done similar kind of calculations.
Yes,
Just
sir,
go
yes,
back. It's exactly similar to that. What we have done earlier.
Sir, the state omega and state 0 belong to different Hilbert space. I mean, how can we write inner product between them?
I don't understand.
I mean, state omega belongs to the basis state of H hat. I mean, energy eigenstates, and H hat and H naught hat, they have different space. I mean, different set of energy eigenstates that don't belong to the same Hilbert space. So should there be an inner product? I mean, between omega state and 0 state.
The H hat naught is a Hamiltonian. It has some states, and you know what those states are, and you know what I've given you an interacting Hamiltonian. You don't know what those states are, but you denote them by those states by some k10s, and you calculate the inner product between k10 and k0. So what's the problem with that? I don't get any problem. I don't see any
Okay, sir.
problem.
My confusion is clear. Yeah, I understood. Yeah.
There are two means. I don't really understand what you are saying. Anyway,
I confused it with something else. Okay, sir, I understood.
see here you can consider this as only one. Both of them have the same, so to say, Hilbert space. Or what you can say is that the Hilbert space for the full interacting Hamiltonian and the Hilbert space for the free field Hamiltonian. That Hilbert space, the states in that Hilbert space, you know their forms. And the
Yes.
state full interacting Hilbert in the full interacting Hamiltonian, those states in that Hilbert space you don't know, but those are also state vectors, ket vectors,
Yes.
and they will have inner products with this. You can always define inner products between those states for a interacting Hamiltonian and states of a free field Hamiltonian. There should not be any difficulty in defining inner product between those two states. Only difference is that you don't know what these ends are.
Yes.
That is the problem. You can think it in terms of single particle Hamiltonian in quantum mechanics. You consider a single oscillator, free oscillator in quantum mechanics. You know their eigenstates and energy eigenvalues. Now you take the oscillator and put a harmonic anharmonic potential x to the power of 4 potential. Then also there will be some states, and those states will have inner product with the states of the three oscillators. There is no problem. There is no dimensionality problem. It is a one-dimensional oscillator.
Yes, sir.
The Hilbert space of both the free and the interacting oscillators are one-dimensional. So there are states there, and there are states here. They will have inner product. What's the problem? Okay. So what we have now is we have an expression of this form. E to the power of minus I h bar h hat t get 0 divided by, see, if you go, I am repeatedly telling you that please go to your path integral notes. That may help you. See, if you remember, we have derived similar kind of expressions when we were discussing path integrals in quantum mechanics. We had similar kind of expression, and now you can see that this is a pure number. This is some number, okay? And you don't know what this number exactly is because there is omega sitting over here. But you don't need to know also that number, because you can get rid of that number by dividing by omega, ket omega bra omega. That will take care of the normalization. You can just, at the end of the calculation, you can just divide it by ket omega bra omega. That will be that will take care of it. But why is this result important? It is important because you can see that ket omega now gets related to the ground state energy of the free field Hamiltonian. And you can now write this thing, the ket omega 0. So you can write this as h hat not t, because h hat not acting on 0 is 0. Therefore, this factor is 1. So you can always introduce a e to the power of I, this factor here. But what is this operator? This operator is nothing but u hat e to the power of I h bar. So that operator is basically u hat dagger of minus t, if I am not mistaken. So let us see what u hat is. U hat t is e to the power of I by h bar h naught this. So if I take a dagger, then what will happen? If I take a dagger, then I will get plus h this. But the expression that appeared there was plus I h naught t and minus here. So it's basically minus. So this operator that I wrote down is nothing but u hat dagger of minus t. So you can now relate k omega, that is the ground state energy of the full interacting Hamiltonian, to the ground state energy of the free field Hamiltonian in terms of the unitary operator u hat, which evolves via the interacting part of the Hamiltonian in the interaction picture. So you know what k omega is, you know what phi's are, and therefore now you can put everything in the time order product vacuum expectation value that you want to calculate and proceed and see what you get. So this we shall do tomorrow. Please go through what we have done today, because this part is very important. This is the formalism part, and you should be very, you should feel okay with this formalism. So let us end here today.